Hello everyone and welcome to this video.
Imagine you are hired as a data scientist by an online bookstore eager to enhance its recommendation system. Currently, they rely on trending titles and editor picks, but they want something more personalized. Your mission is to build a recommendation system using non-negative matrix factorization. This system will learn hidden patterns in user preferences, predict how users might rate books they haven't seen yet, and suggest books each user is likely to enjoy. Let's dive into how we can achieve this. Now, let me explain the algorithm we're going to use to solve BookHive's problem. Non-negative matrix factorization, or NMF, is a powerful technique for dimensionality reduction, often used in recommendation systems. It breaks down a large matrix into two smaller ones, capturing the essence of the original data. In our case, the matrix represents user book ratings, with rows as users and columns as books. Most entries are missing because users haven't rated every book. NMF helps us approximate this matrix, filling in the gaps with predicted ratings. This way, we can suggest books to users based on these predictions. Let's get started by importing the necessary modules. I'm going to import the essential libraries for our project. We'll use pandas for data manipulation, NumPy for numerical operations, scikit-learn's NMF for our matrix factorization, and matplotlib for visualizations. Let's import our dataset to see what we're working with. I'm going to load our dataset into a data frame called ratings_df and display the first few rows. As you can see, our dataset contains three columns: user ID, book ID, and rating. Each row shows how much a user has rated a specific book. Now, let's find out how many unique users and books are in our dataset. I'm going to calculate the number of unique users and books in our dataset. This will help us understand the scale of our data and the diversity of interactions we have to work with. Now, let's create our user item matrix by pivoting our dataset. This matrix will form the basis of our recommendation system. I'm going to pivot our dataset to create a user item matrix. This matrix will have users as rows and books as columns, with ratings as the values. This is the structure we'll use for our NMF model. Now, this is our user item matrix. As you can see, most of the values in this matrix are empty, indicating that not all users have rated all the books. Let's fill these non-values with zeros to prepare the data for NMF. I am going to fill these empty values with zeros. This step is crucial because NMF requires a complete matrix to work with. This is our matrix A. Now, let's apply the NMF algorithm to it. I'm going to apply the NMF algorithm to our filled user item matrix. We'll decompose it into two matrices, W and H, which represent user features and item features respectively. This decomposition will help us predict missing ratings. The init parameter in NMF is crucial for starting the factorization process. We've used NNDisVD, which stands for non-negative double singular value decomposition. This method provides a smart data-driven initialization of the matrices W and H, leading to better convergence, improved results, and more stability, especially on sparse datasets like ours. Now let's calculate the product of W and H to get our predicted ratings matrix. I'm going to calculate the product of the matrices W and H. This will give us a dense matrix of predicted ratings, showing how a user would rate a book if they had read it. Now, as you can see, this matrix is dense and contains non-zero values that represent the predicted ratings. It shows us how a user would rate a book if they had read it. Now, let's define a method to recommend books to a user. This method will generate top-end book recommendations for a given user by identifying books the user hasn't rated yet and using the predicted ratings to find the highest scores. So let's go ahead and define a function called recommend books. This function will take a user index, the original ratings matrix, and the predicted ratings matrix as inputs. It will return the top N recommended book IDs for that user based on the highest predicted ratings for books they haven't rated yet. Now, let's try out our recommendation function with a random user ID to see how it works in practice. I'm going to test our recommend books function with a sample user index. This will give us a list of book recommendations for that user based on the predicted ratings from our NMF model. I am going to use a for loop to print out our predictions. We can see that if this user reads the book with a specific ID, they would likely rate it highly. This makes it a strong recommendation for them. Now, imagine your boss has asked you how to evaluate the performance of this recommendation system. A simple and effective way is to check how close the model's predicted ratings are to the actual ratings that users have given, but only for the ratings we already know. This is where root mean squared error comes in. It measures the average difference between the predicted and actual ratings. A lower RMSE means the predictions are more accurate. Let's take a look at the code to calculate it. I'm going to define a function to compute the RMSE between the actual and predicted ratings. This function will flatten the matrices, drop naive from the actual matrix, and calculate the RMSE only for the known ratings. Let's run this evaluation to see how well our model is performing. The average difference between the predicted and actual ratings is around 4.5. This suggests that our recommendation system isn't performing very well at the moment. Now, how can we make it better? This is where parameter optimization comes in. By tuning the model's parameters, we can often make significant improvements. One key parameter in NMF is the number of latent features, or N components. Let's see how different values of N components affect the model's accuracy. I'm going to run a loop to test different values of N components, which represent the number of latent features in our NMF model. For each value, I'll fit the model, predict the ratings, and calculate the RMSE. This will help us find the optimal number of components for our recommendation system. I'm going to run this. This might take some time as we are training our model 6 times to find the optimized parameter. Please take a moment to like this video, as it is going to be a great help, and don't forget to subscribe to my channel. Now, let's visualize the relationship between the number of components and the error, or RMSE. I'm going to plot a graph showing RMSE versus the number of components. This visualization will help us understand how increasing the number of latent features affects the model's accuracy and guide us in choosing the best value for NN components. We can see that as we increase N components, the error tends to decrease. This means the model is capturing more subtle patterns in the data. However, we should be careful not to overfit the model by choosing too many components. A good trade-off between performance and efficiency seems to be around N components equals 55. It gives us a significantly lower RMSE without the added complexity of going too high. Amazing, you now have a working NMF-based recommender system and a basic understanding of model tuning and evaluation. In future tutorials, we'll explore other use cases of NMF, starting with topic modeling for text data.
Thank you so much for watching this video. Don't forget to subscribe my channel and see you next time.